second half, and we're going to wrap up wind. So I'm just going to blow through the figures, hit the highlights, tell you what you need to know for the exam, and then do you have questions on the second problem set to look into?
Second problem set?
Yeah.
Maybe.
Okay. Well, we'll dig into that afterwards. So we'll just finish up the chapter, and then we'll do problem set 2 and call it a day. So what we're looking at here are just different shapes of wind foils. The guiding principle behind all of these is Bernoulli's equation. And let me bring that up right now. What's going on at MIT today? The arts, nice. Hey, what's going on, Kat? Oops, let me get myself connected. Oh yeah, don't sit in the sticky seat. Do you want, Tyler grabbed this nicer one. You want to sit here?
Oh, very nice.
It's the cushy.
Where the heck did he get that?
It was sitting over here. It was the.
That's hilarious.
But you can't really sit down up here, so.
Yeah.
All right, so I'm having.
Oh, yeah. Speaking of Tyler, sorry to interrupt you.
Not at all.
He said that.
All right, we're back. So what we're looking at here are different airfoil shapes, and what I want to show you is a little bit of mathematics that really drives all of the physics here. And what I'm going to show you is the Bernoulli's equation, and help you decipher it a little bit. So here it is in all its glory from hyperphysics, good reliable source. And what we're looking at is two sides of an equation. And what I'm going to try to tell you is that this really is when it comes down to it, it's more or less a different version of the first law of thermodynamics. So at its base level, it's actually an energy equation. So let's just go ahead and write it down. So P1 plus 1/2 rho V1 squared. So P, I'm going to use little p, 1 plus 1/2 rho V1 squared plus rho GH H1 equals P2, and be careful that you're writing your P's as P's and your rhos as rhos. And again, rhos is R-H-O, that's the Greek letter rho, and it stands for density, as you may know, plus 1/2 rho V2 squared plus rho GH2. Got her? So the two sides look the same. So it's just in words, it's P1 plus 1/2 rho V1 squared plus rho GH1 equals everything that I just said. Just replace the ones with the twos. And so kind of looks like a lot, but we're going to break it down into 3 components, and this is going to take us right back to Energy 101, Chapter 4. So first of all, what's this guy look like in terms of energy? What kind of energy is that?
Density and velocity.
You got velocity, you got density. What happens if you replace that density with mass? What's 1/2 mv squared? What kind of energy is that?
Kinetic.
It's kinetic energy. Yeah, it's kinetic energy. and we can do a nice little easy demonstration of kinetic energy. Here it is when I throw the eraser through the air. It's got kinetic energy because it's moving, right? What's the next one? And again, let's just replace this. Let's replace the rho with mass. G is gravity and H is height. So what's mgh instead of rho gh?
Gravitation.
Yeah, gravitational potential energy. So I'll just write it out as gravitational potential. And again, using the same very simple, right now, the eraser has a certain amount of gravitational potential energy. I release it, it loses that potential energy and it becomes kinetic. Okay, so we're familiar with those two types of energy. What's the first one though? What's that P? What kind of energy is that?
This is would be potential.
It's pressure. You might call it potential. But really it's elastic energy. It's elastic energy.
And that is,
So elastic energy. So I've got this is a spring. I deform the spring. Hold on. I deform the spring, and it comes back. So I put some mechanical energy into that. I put some work into it, force times displacement, and that energy was stored. So it's a spring. It's elastic energy. So air, which is what we're talking about, when we go back to our airfoils, has elastic energy, and it's the elastic energy in the air right now that's allowing you to hear my voice. I'm sending pressure waves from my mouth to your eardrums that's conveying information. So again, what we're looking at in the equation is that whatever's happening, and they call it pressure energy, but same thing, elastic pressure. Air is a spring. Think of air shocks on your car, right? Pressure plus kinetic plus potential, it's just saying that as I move air through a system, and here's a system, whatever you give up in one place, you're going to gain somewhere else. So at this point, we are assuming that the density doesn't change. If you look back at our equation, we'll see there's not a rho 1 or a rho 2. We're assuming that the density doesn't really change. Truth be told, it does a little bit. Any pressure wave is going to change the density of air. That's how it works. You smack it, and the molecules get closer together, and that's what creates the wave, or the molecules in the air just smacking into each other. But it says that whatever you give up in pressure, maybe you gain in height. And that's essentially why you have lower air pressure higher up. Whatever you lose in velocity, you might gain in pressure. So again, as a wave smacks into a wall, velocity stops, well, the pressure just went up.
yeah.
So those are the three types of energy that are being exchanged in any fluid system, and that's Bernoulli's equation. Not sure we're going to have to solve that bad boy, but this was major breakthrough physics a couple hundred years ago to actually be able to write this thing down and talk about gravity, talk about density, talk about velocity, talk about pressure, put them all together, and away we go. Now we can make predictions.
So the way to kind of state that simply is like that if you put all those different types of energy together, then it increases, like through a system? Or you're saying that if one decreases, then the other increases?
Absolutely. If one increase in a closed system, if one increases, another one has to decrease. It's more or less a restatement of the first law of thermodynamics.
Is that inverse?
You could call it an inverse relationship. Yeah. You could call it an inverse relationship. Maybe inverse is not the right word. Inverse typically implies multiplication. Maybe a better way would just be displacement. If you push somewhere, it's more of a, thus the addition. We're adding these together. We're adding them together, so it's a conservation law. 3 types of energy in one system. So as you can see in this little Venturi tube, you can see that remarkably, you might think, oh, this air is moving through this tube. Oh, all of the molecules are all packed into that one little spot. The pressure must go up, right? Well, no. The velocity went up, so the pressure actually went down. The pressure actually went down. And that is exactly what makes these things go up. So it's farther to travel. The air molecules are being pulled apart, thus providing lift for the wing. In this case, since the wing is symmetrical, you're not going to get lift or drag unless you give it an angle of attack. If you ever watch the biplanes, the trick planes that they'll actually have their wings shaped symmetrically so they can fly right side up or upside down. They control their lift with little flaps on the ends. But in general, if you look outside, that's the wing you're going to see on your airplanes. This is the wing you might see on a bird's wing. This is what you might see in a fish. So anything that's moving through fluid has some kind of shape. It's going to have some lift. It's going to have some drag. Okay. Now, this guy is showing us that as we change the angle of attack, the lift increases. So as we get this angle of attack higher and higher and higher, the lift increases. The drag's also going to go up a little bit too. So as this guy, all we're doing is we move along this axis right here. We're just tilting this wing up, 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 up. The drag goes up because, here comes the wind. The drag is going up because you got more area, but the lift also goes up as well. Divide those two numbers together, and that's your lift divided by drag. At some point, you hit an optimum. And as soon as the engineering mind says, "Oh, I hit an optimum," that's what you get excited about. This is your double bottom line. For hey, I've got my lift isn't maximized. My maximum lift happens over here, but my drag is still low, so the lift to drag ratio is optimized. Now I've got my best fuel efficiency for my airplane. I'm saving jet fuel. Do the long haul better. So just knowing these two relationships, well, there you go. Another very important equation to know. I think this is in the book, but I just want to talk about it while I'm thinking about it. Is the force of drag equals 1/2 C, let's call it A, times A, rho V squared. So we know what 1/2 is, we know what density is, we know what velocity is, we have a pretty good idea of what area is. This guy right here, C sub A, is essentially what we're looking at in this equation. It's the drag coefficient of it's C sub D. Let's rewrite it. It's also C sub D. So if we have some wind coming at some velocity, and we have some structure with some area, I'm just drawing like a square parking sign or whatever. Obviously, when the wind blows, there's going to be some force. The bigger the sign is, the more force it is, right? Of course, make that sign bigger, there's more force. Make the air more dense, flow water over it instead of air, there's going to be more force. Blow even harder or flow even harder, more force as well, goes by V squared. So more area, more density, more velocity. this is the sort of the tricky bit, because this guy, this stop sign, is going to have a C sub D equal to 1. Typically, in general, you're just going to call this C sub A because it's the drag coefficient, or it's the coefficient of friction, or fluid friction, if you will. If, however, I come up with a more streamlined shape, I get some velocity going, my C sub D can be closer to 0.1. Now, I can't help myself, I've got to show you this.
Could you explain a little bit what the coefficient is?
Yeah, absolutely. There's a human being inside that bicycle going 80 miles an hour. He's not going downhill. There's no tailwind. It's just a guy in a bike pedaling his lungs out, going 82 miles an hour, like really happened on planet Earth. He's not drafting behind a car, start to finish. So his drag coefficient, per your question, is very low. So the force pushing him backwards was also very low. So let's just hop on this again. Again, very important. So force of drag equals 1/2 C sub D A rho V squared. So let's just do a little dimensional analysis. So if we go back to Newton's second law, we know that F equals ma. So F equals m. So there's our m. Acceleration is length over time squared. The dimensions of 1/2 are just 1. It is dimensionless. We're going to leave C sub D alone for now. We know that area has dimensions of length squared. We know that density is mass per unit volume, so that's mass per length cubed. And we know that velocity is length over time, so velocity squared is length squared over time squared. Okay, now we're trying to figure out, what is this C sub D thing? Well, what is it? Well, we can scratch that out. Scratch that out. Scratch out the M. Scratch out the M. Now we've got, what do we have? We've got L to the, let's just see what this guy becomes. This becomes L to the 4th. L to the 4th power over L cubed equals L. Now we can just scratch the L out. So, what are the dimensions of C sub D? What are the dimensions of the drag coefficient? I don't have any dimensions left. It's got to be 1. It's dimensionless. The drag coefficient is dimensionless. And you could write it like this. We could also say C sub D equals, like if you were trying to figure out what C sub D was and you were measuring everything else, like I know how fast I'm going, I know how big I am, I know what the density is. What's C sub D? Well, it is 2 times the force of drag, I'm having some deja vu right now, over the area, over the density, over the velocity squared. So you set up you stick your bicycle in your wind tunnel. You measure how much force is pushing on it, how fast is the wind blowing, what's the density of air, and how big is it. That's your C sub D. Another good way to think about it is it's kind of like efficiency. Typically, so C sub D is always greater than 0, and it's almost always less than 1. You can design structures that are worse than 1, but it's kind of, make sense? It's aerodynamic efficiency. Cool. Yeah. Okay. This is just showing how wind flows around an airfoil. Again, nature abhors a vacuum. You've probably heard that before, so the molecules are going to fill in wherever they are. This is a vortex. It's this little guy. So right here you can see, going back to Bernoulli, here's your velocity. I got a lot of velocity. Boom, I hit that. Well, I gave up velocity, but I gained pressure. So now I've got pressure pushing me up. And that Bernoulli's equation is happening at every single place all over. So you might say, well, where's V1? Well, it's over here. Well, where's V2? Well, it's over here somewhere. So that Bernoulli's equation is happening throughout the entire system. And again, you just have to define where those system boundaries are. All right, now what we're doing, it's kind of a cool figure. It's a couple projections. So there's your eyeball, right? And you've got a wind turbine, and I've got, my hand is here. I'm going to maybe pretend I only have, three fingers. But what I'm doing, I'm sort of looking down on one of the blades. So when I look, and so the wind is being shown as sort of coming at the page. So the wind is coming towards the wind turbine blade. Obviously, it has some radius. Way out here at the tip, the radius is the greatest. So now if we're looking down at the blade, the blade is flying through the air, right? It's in a circle. But what's being shown is that there's this lift force, and this is the important part. The lift force is sort of pulling the blade forward. It's almost like the wind turbine wants to fall forward. All right, so just imagine you've got here's the tower, here's the blade spinning around. It almost wants to just pull itself into the wind. It doesn't, because it's on a tower. The important part, though, is that this lift force, when designed correctly, pulls the blade forward in the rotational sense. So the turbine wants to fall forward, but the blade with that lift also wants to keep spinning in a rotational forward sense.
So basically, it redirects the energy. So instead of being forward, it's...
Yeah, you can think of it as redirecting the energy. Absolutely. Yeah, in the same way that an airplane, the thrust is, the energy is going out the back, but yeah, the energy is redirected and it pulls it up into the sky. Yeah. So that's the fundamental principle of a horizontal axis turbine, or any lift-based turbine. Remember last time we talked about Darius versus Savonius. Darius are always lift-based, Savonius are always drag-based, so this is a lift-based.
It's funny, I was just going to ask why we're learning about all of that. I was like, why are we learning about airplanes?
Oh, yeah? Well, I know, yeah.
It makes sense now.
Well, it's weird. I mean, you look at the turbine, like, it's just an airplane that's not going anywhere, all right? It's just
Exactly, yeah, I see that.
Yeah, it's an airplane. And winds and propellers have to obey the same principles. The propeller spinning, the wings not really spinning per se, but it's obeying the same principles.
Yeah.
Okay, now if we look at a turbine blade, in fact, I woke up in Belgrade, Montana this morning, looked out the window, and there were several of these going right by the hotel. And what they typically do, these blades are long enough that they'll span 3 rail cars, so that the tip and the root are on the car number 1 and car number 3, and car number 2 is just hanging out, not doing a thing. Kind of cool. See the wind turbine blades going. And it was moving. That train was rocking too. So what we're seeing, though, at the tip of the blade, the apparent velocity is much greater than at the root. So I don't know if you guys ever played vinyl records or whatever. You see the record spin. So at the very center, what's the velocity? Well, it's 0. It's not going anywhere. It's just spinning. At the outside, it's got its maximum velocity. So each one of these little vectors is just showing you, as you move further out, the velocity changes. And if we go back here, we can see, well, the force also changes. So that's why get that blade bigger and bigger, more and more force, because it's moving faster out at that tip. And that's why we see wind turbines grow as large as they do, because it's a function of the velocity. Another important relationship to know. Pretty simple, but let's just take a look at it. We've got a, if you guys, did you take the practicum already, Daniel?
Yeah.
We're gonna take some turbines up to Browning and let them rip this summer. So if you're interested, I don't know, we might do it here in Missoula too. But the equation we're looking at here is R, so that's the radius, and R changes. Obviously moved out. This is the I'm just going to use U. That's the apparent velocity that we just saw in that last figure. It's also velocity. It's just let's not call it V because that's the wind speed. And then the third thing to keep in mind is omega. So, and that looks like a W, but it's omega. So we know that U equals R omega. Very important equation in any kind of spinning machinery. And it tells you that the velocity equals the radius times the angular velocity. Velocity. And so, again, velocity is measured, sorry.
No, you're fine.
Velocity equals radius times angular velocity. Angular velocity. So velocity is length over time. Radius is length. So angular velocity is 1 over time, and this is going to be measured in either hertz or RPMs. And hertz is always radians per second. So, and getting back to a circle, this will help you out when you do Euler's formula. 1 radian is 1 radian. It's about 57 degrees or so. And so there are 3.14 radians. This is where pi comes from. 3.14 radians. There's 1, 2, 3, and there's your 0.14 radians right there. So you can easily convert from revolutions per second, like how many times it goes all the way around, or per minute, to radians per second. Those are the two most common dimensions for angular velocity. You can't measure it in miles per hour, you can't measure it in pounds, you got to measure it in hertz or RPMs.
So it's revolutions per minute?
Yeah, revolutions per minute. And that's what you see when you're in your car. You look at the tachometer, 2,000, 3,000 revolutions per minute. That's how many?
RPM is?
RPM, yeah.
Oh, that's funny.
Yeah, when you see that 2,000, 3,000, that's how many times the engine spins every minute. Yeah. Yeah. Okay. What's next? Oh, wait, now, if we look down, now we're actually looking straight down at, so we just covered the physics of a horizontal wind turbine. Now we're looking at the physics of a vertical axis wind turbine. Here comes the wind from the left. We've got our blades. Each one of these little blades is an airfoil. At every single point along the circular path, the lift and drag coefficients change. If we look at this little guy here, we can see that so this is the equation I just gave you. U equals omega R. They used big omega, I use small omega, no big. So this guy right here, this U is the apparent wind velocity. This guy right here, V1, is the actual wind velocity coming into the turbine, and you add these two vectors together. Let me show you that, in case you're not familiar with vector addition. So if I have vector A, vector B. These are both vectors. I'm going to put a little line under them. A plus B equals, there's your A, there's your B, and there you go. This is A plus B. So I've got, the vectors they're in 2 dimensions. They're not numbers. They have lengths, but they've got 2 directions. So if I, and you can think of it, hey, I want to get to the corner of Higgins and Main, I'm going to add up a bunch of little vectors. First I'm going to go on 3rd Street, then I'm going to go on Higgins, et cetera, et cetera. I add all my vectors together, and I get to my destination. You can think of A plus B as the distance as the crow flies, for example, to borrow a phrase.
Oh, I see.
A plus B. So you're adding. We just did it. We just did vector
And then
addition.
it gives you that third.
That third one is A plus B. Exactly. So that's what each one of these guys is. This W is what the blade itself is seeing as a result of the fact that the wind is blowing and the turbine is spinning. Yes.
Could you kind of explain a little bit more what the construction is like of this? Just
Sure.
because there's nothing connected, it's confusing.
Yeah, for sure. It's It's just one of these guys.
Out in front of the
Yeah,
gym over
yeah,
there.
these
I
are,
know what you're talking about.
yeah, these are kind of, it's, that's a Savonius style, so it's a drag based. I'm trying to find one that's more,
Interesting. So it tries to capture the wind moving upward?
Nope.
Or- No, side to side.
Yep.
either way.
yeah, so we're looking at one of these guys right there. This one has 3 blades, the one we're looking at here has 4
Like it's
blades.
tipped like we're looking at it from the top down?
We're right above it looking down at it.
Okay,
Yep,
gotcha,
yeah,
that makes sense.
exactly, yep, absolutely. So now what we can see is, and we already did lift and drag. We know that they're perpendicular to each other, always, by definition, just like X and Y. And so at each point, well, here's the lift, there's the drag, here's the lift, there's the drag, there's the lift, there's the drag, there's the lift. So the lift and drag vectors are changing all the time, all over the map. But you can see that this lift vector is more or less in that direction. It's pulling it forward. This lift direction, yep, same thing. This one, sort of, not really, a little bit. And this one almost nothing. I mean, right here, you're like, oh my gosh, all my force is backwards. Because this lift in that direction, it's just pulling the thing outwards. It's not pulling it in the circle. But on average, when you add them all up, the thing spins.
Yeah. You can kind of see, like, angularly, it makes sense, like, this one in the bottom left,
Mm-hmm.
if it goes up, then that angle would change the exact, and then it just flips when it
Yeah.
gets to the other side,
Yeah.
and then vice versa.
Yeah, and if we took this whole thing and like turned all the blades around so they're pointing backwards instead of forward, it would just spin the other direction.
Yeah.
It's as simple as that. Cool. That's how they work. Okay, now every single wind turbine, and there is a relatively sophisticated problem like this, either on the exam or on the final exam, and it asks you to figure out the average power of a wind turbine given an average wind velocity. So right here, if I said, gosh, what's the power of my turbine at 10 meters per second? Well, there's my 10, about a kilowatt, right? What's the power at 5? Well, let's see, there's 1, 2, 3, 4, 5, 100 watts, all the way up to, gosh, 15 meters per second, 30 miles per hour. I'm knocking on $2,000. I'm at a little over 1,700 watts. Now, at some point, the generator just can't make any more juice, and this is it's maxed out. There's only so much capacity for electrons to flow in the wires, and there you go. And at some point, like, oh my gosh, if this thing keeps spinning, it will blow itself apart. Like literally, there's enough centrifugal force, and I've built turbines before that watch them fail. It's kind of fun. So
To a certain speed, it'll shut itself down.
yeah, and there's different ways to do that. One typical way is if you've got, here comes the wind at my hand, it's spinning happily, but once it gets heavy and, the wind is blowing hard enough, there's some kind of neat mechanisms where the, I don't know if you remember the old saloon doors that kind of hinge back and forth. Well, they're on a little helix.
Okay.
The bearing travels up and down on a helix to make the thing go back down to, its lowest potential. Well, once it blows hard enough, the entire turbine spins sideways and the air just slips past it rather than spinning it apart. Yeah. And it's just very simple mechanical hinge spring, if you will.
Right.
Yeah. There are other ones too that say, hey, let's just take the blades and rotate them 90 degrees. That's how most of the big boys operate. They, got motors in there to change the angle of attack. Okay, now this is just more or less a histogram. So think back to that drag and lift equation. So what we've done here is multiplied the probability of finding a certain wind speed by the power at that speed. So we've multiplied this curve. Let me do it. So what we've got is, so we just looked at the power curve, right? We started here, went up. Oh, and the other reason this thing curves up like this, it's because of the V squared. Actually it's V cubed, beg your pardon, V cubed. So power, power, big P, power, is proportional to the velocity cubed, and we derived that last time. So the power in a turbine is proportional to V cubed. So here's V, here's P for power. Now, what we're looking at is, here's V, and here's T. So let's just say, gosh, at 9 a.m. and this at 9 a.m. the average wind velocity. Here's 0, here's 5, here's 10, here's 15. Let's just go out to 15. 5, 10, 0. Sorry, it's not really to scale, but you get the point. 0, 5, 10, 15. 0, 5, 15. We go out with an anemometer, measure the wind speed, and say, gosh, early on the velocity was 5 miles per hour. I'm going to put a little box there. I went out later. Ooh, it looks like it was blowing more. Oh, it really picked up. Then it died down. I'll put another one here. Died down a little bit more, and then it died down again. I come back the next day. Oh, and let's just say it was relatively calm, so I got mostly 5 miles per hour of wind. Come out the next day. Oh, it's really windy. Some of this, a little bit of this. Eventually, I end up with sort of a bell curve of wind distributions, and this is what you're going to do anytime you're going to go out and sight or somewhere. And what you want, you want to say, yeah, I've got a lot of good wind out here. We were just driving from Missoula to Billings yesterday, and a buddy of mine was pointing out an old wind farm where they built the thing because it was really windy, but it was too windy and they all blew down. It just didn't, so at some point, too much.
Like the guest speaker that you brought in, who was talking about his
Jackson, yeah.
Stuff in Alaska.
Yep, yeah. It's all machines have their limits, but so this curve is the product of those two curves. So this times this equals so you end up with velocity, you end up with power, you end up with something like this. Because let's just say that the wind never blew at 45 miles per hour. It just didn't happen. The wind probably blew at 0 a bunch, but where there's no power. So you might have, gosh, it was off for a lot. You had all these off. You could have all these, bins of 0 wind. Well, 0 times anything is 0. Now you take this guy, and we know that energy equals the integral of power over time. That's what that is. So all of this is energy. So the longer your turbine runs, the more energy it collects. And we also know that the money, and you're doing this, you've been doing some of this in 214, Daniel.
Yeah.
The money equals the dollars per kilowatt hours times kilowatt hours. And that's exactly what energy is. Energy is measured in kilowatt hours. So the longer it runs and the more energy is worth, the more coin you make. If you're running carbon credits, you might get some of those too along the way.
Do you know how the university is buying carbon offsets?
No, do you?
No.
No, it's been a struggle. It's been a real struggle. The university is not flush with cash, and George Dennison, when he was in office, said, "Hey, we're going to follow the Kyoto Protocol. We're going to go carbon neutral by 2020." Royce was there for a little bit, and then the folks I mentioned previously said, "No, you don't. You're not going to divest on my watch." I think, and that stuff does not make the news. I mean, that happens in back rooms and coffee shops. It just doesn't happen because we're gonna turn off your cash flow if you turn off our carbon drip. I mean, it's as simple as that. And I know, the former sustainability coordinator resigned because of the lack of transparency there, and the current one, Eva, I think she's doing her best, but I think she's getting mired down too with a lot of stuff. So can't keep fighting the good fight though.
Do you still want to come to Sustainaganza?
When is it?
It's the 20th of this month. So next.
Is it down at Free Cycle?
Nope, that's Earth Day.
Oh.
You should definitely still go to that too.
Okay.
That's like the 22nd.
Okay.
But Sustainaganza is here on campus.
Yeah.
And so my student group and if you've met and talked with Lily,
Yeah.
her student group, we're going to get together and do a table.
Cool. Yeah, let's do it.
So,
Yeah, I'll be
yep,
there.
we're
Cool.
advocating for you, Brad.
So it's thank you.
Program,
And it's
yeah.
so it's in 1 week.
Yep.
Thursday?
Yep.
What time?
I don't know.
Okay.
In
All
the
day?
evening, I think it's like noon to 4 or something.
All right.
In the
Well,
DC.
maybe we'll have we'll have
Bring some gizmos.
we'll have lecture down there.
That would be cool.
Bring
Thanks.
some gizmos. Yeah.
Yes.
Solar panel. Okay.
Cool.
All right. Thanks.
Sorry to interrupt.
No, it's cool. A little bit more here. Last couple things. So this is the curve I was just showing. The distribution curve, that's what I just showed right here. That was figure 30. And then this is also just showing wind frequencies. So that curve is basically this same curve as a function of space. Multiply them together and you get total energy expected, total energy audit. And then this is also showing environmental effects. So if you've got your turbine right next to your house, the decibel level goes up. I don't think they've got it. Yeah. So it might get as high as 45, 50. And this is also an R squared value. Decibels are rated on a logarithmic table. That's why they appear linear on this scale. And there we are. The farther you are from the turbine, the less likely you are to hear it. I guess when you get out far enough, it just sounds like falling leaves. So, okay, we'll take a break there.